In this video, I'm going to prove that there are an infinite number of primes. There are infinitely many prime numbers. And this proof is going to be, hopefully for many of you, non-standard. That is, a proof for this theorem that you've never seen before. Which is one of the reasons why you should definitely subscribe to my channel. I do, even if you know a lot of the proofs of these theorems, maybe you'll see a new one. Maybe you'll like it. K-proof. Let. Now, not going to start from the top because I want you to see a pattern. Suppose I tell you that n sub 5 is n1, n2, n3, n4 plus 1. And n4 is n1, n2, n3 plus 1. n3 will be n1, n2 plus 1. n2 will just be n1 plus 1. And n1 will be the number 2 itself. And in general, n sub k will be n1, n2, up to nk minus 1 plus 1. Okay. Now, I claim that the GCD of any two of these, say m sub j, n sub k, is equal to 1, providing n and k are different. That is, I can't argue that the GCD of n4 and n4 is 1. The GCD of n4 and n4 is n4. But I want to say they're different, and to make my life easier, I want to say which one is smaller. J is smaller than k. So let us prove this claim. Suppose otherwise. Suppose the GCD of n sub j, n sub k is equal to d. Now I want to show that d is 1. Okay. This would imply that d divides n sub j and d divides m sub k. After all, d is a common divisor of those numbers. It's also the greatest one, but it's a common divisor. Now, n sub j will divide n1, n2, up to nj, and then beyond, up to n sub k minus 1. Why? Because nj is one of the factors. Just for the record, nj could be k minus 1. Shucks, nj can be n1. nj is one of the factors from n1 through nk minus 1. But now, if d divides nj and nj divides this, that implies that d divides n1, n2, up to nk minus 1. Now, we know that d divides this and that d divides that number. That implies that d will divide m sub k minus n1, n2, up to nk minus 1. But what is that? nk is n1, n2, up to nk minus 1 plus 1. Ooh, and then I take this away. I take away n1, n2, up to nk minus 1. Okay, take that away. Oh, I get 1. That implies that d divides 1, but that implies that d is 1. That is the GCD of n sub j and m sub k is 1. They have no common factors. They have no common primes. Okay? So now, each of these numbers are bigger than 1. Each of these numbers are bigger than 1. So let's write that down formally. Note that each m sub I is greater than 1. That implies that there's a pi, there exists a pi, such that pi divides n sub I. But pi does not divide m sub j, where I and j are different, because the GCD is 1. The GCD of ni and nj is 1. They have no common factors. So if pi, prime or not, is that goes into or divides ni, then pi can't divide nj. So for each m sub I, there exists a different prime. But we could make up infinitely many ones of these. We can make up infinitely many ones of these. Because now I have n sub k. That's n sub k. Nobody can argue that. There's an equal sign that says that's n sub k. So this is a known number. So n sub k plus 1 is nothing more than this known number, which happens to be denoted by m sub k, and then I can add 1 to it. Nobody's saying that these numbers are prime. Some may be, some may not be. If I'm not mistaken, it's an open question whether or not there's an infinite number of these. If there's of these type of numbers, are there infinitely many that are prime? Because some of these numbers are not prime. Like here, 2 n1 is 2. n2 is n1 plus 1, which is 3. That's not prime. n3 is 2 times 3 plus 1, which is 7. That's not prime. n4 is 7 times 3 times 2 plus 1. That's 43, which is not prime. Which is prime. n5 is 43 times 7 times 3 times 2 plus 1. 42 times... Oh, that doesn't work. Okay, 42 squared. Oops. Is 1600. Is 1775, if I'm not mistaken. And let's just argue it from a different point of view. 3 times 7 ends in a 1. 1 times 3 ends in a 3. 3 times 2 ends in a 6. You add 1, it ends in a 7. Darn. Oh. I forgot to add 43. So let's just do it. 126, 168, or 1806. Plus 1 is 1807. And I don't know, but I'm telling you, not all of these numbers are going to be prime. Not all of them are prime. Okay, so that's, if I'm not mistaken, it's an open question if there's going to be on that list an infinite number of primes. If it isn't an open question, it was recently solved. But once again, for every one, for each ni, there's a different prime. But there's an infinite number of n sub i's, which implies there exists an infinite number of primes. Now, I know I verbally said it, but did I say that there's an infinitely many ni's? So I should say, but there exists infinitely many n sub i's, one for each integer. That implies there's an infinite number of primes. See you guys in the next video. Hope you enjoyed this proof. Watch and learn.